So let's talk about the Google File System, or GFS. And look, this isn't just a story about code and servers. It's really about a completely radical idea that was born out of pure desperation. Google was facing a data problem so huge that the only way forward was to just throw out the rulebook and start over. And this quote, it absolutely nails it. See, this is what's so fascinating. GFS wasn't just a technical fix. It was a total change in how you even think about building large systems. They didn't just build a better mousetrap. They basically decided to design a system that could thrive in a world that was absolutely overrun with cats.
To really get that shift, you have to rewind the clock to the early 2000s. Google's mission was to organize the entire internet. And that, as you can imagine, created a data problem on a scale no one had ever even conceived of before. All the existing tools, all the off-the-shelf solutions, they were completely useless. They had no choice but to start from scratch.
And the foundation for their solution was built on thousands, literally thousands, of cheap, everyday, commodity computers. Now, this wasn't some grand choice for better performance. It was pure economics. They couldn't afford a massive traditional supercomputer, so they decided to build their own supercluster out of parts that were, designed to fail. And this army of cheap machines had to wrangle petabytes of data. Just try to picture that. We're talking about these massive web crawls, gigantic search indexes. It was like a constantly churning ocean of information that somehow had to be tamed. And here's the kicker. This is the brutal, everyday reality of running that many cheap machines. You could expect about 3 of them to just die. Not per year, not per month, every single day. Failure wasn't some remote possibility. It was a constant, predictable part of the background noise. So this environment of constant chaos creates what you might call an impossible triangle. Think about it. For great performance, you need to split your data across lots of machines. But the more machines you have, the more failures you get, which means you need reliability. You have to make extra copies of everything. But the moment you have multiple copies, you have a consistency problem. Which copy is the right one? And if you spend all your time making sure they're all in sync, your performance goes right out the window. It's this vicious, maddening cycle. So how in the world did GFS break the cycle? Well, here's the genius part. They didn't solve the triangle, they shattered it. They did it by embracing this wild new philosophy. Instead of trying to prevent failure, they would just accept it. They would expect it. They would design a system that was built to thrive right in the middle of it all. And this slide just lays it out perfectly. The old world, the old philosophy, was all about spending a ton of money on expensive, super reliable hardware to try and prevent things from breaking in the first place. GFS just flipped that completely on its head. The new philosophy was to assume, to know, the hardware is going to break all the time, and to build the intelligence to handle it automatically right into the software itself. This whole philosophy got boiled down into a few core assumptions that guided every single design decision. First, and most importantly, failure is normal. Get used to it. Second, their files weren't tiny Word documents. They were enormous, multi-gigabyte monsters. Third, the work was mostly just adding new data to the end of these giant files, what we call appending, not going back and editing the middle. And finally, the goal wasn't a super fast response to a tiny request. The goal was to move massive amounts of data at a steady, high rate. That's it. And these constraints allowed them to build something brutally simple and incredibly effective. Okay, so that's the big idea, the philosophy. But how did that actually translate into an architecture that works? How do you even begin to draw up a blueprint for chaos? Well, it really comes down to 3 main players. First, you have a single master server. Think of it like an air traffic controller. It knows where every single piece of data is supposed to be, but it never, ever touches the data itself. Then you have hundreds of chunk servers. These are the warehouse workers, the grunts, who are actually storing all the data. And finally, you have the clients. These are the applications that actually need to read and write all this stuff. The absolute genius of this whole setup is the strict separation between control and data. A client asks the master, hey, where's the data I need? That's the control flow. It's a tiny, lightweight conversation. The master gives it directions. Then the client goes directly to the chunk servers to get the actual data. That's the data flow. This simple idea prevents that single master server from ever becoming a bottleneck for all the heavy lifting. To manage all this data, GFS chops up every single file into chunks. But here's the wild part. Each chunk is 64 megabytes. Now, to put that into perspective for you, a normal file system on your laptop probably uses chunks that are around 4 kilobytes. So, yeah, 64 megabytes is just unbelievably enormous.
And that leads to the really obvious question, right? Why on earth would you make them so big? It seems like it would be crazy inefficient for anything small. The answer is something you could call the container ship principle. And it makes perfect sense when you think about it. If you have to ship a million tiny packages across the ocean, you don't track each one individually. That would be a nightmare. You put them all into a few massive shipping containers. By using these huge 64 megabyte chunks, GFS drastically cut down the amount of metadata, the number of items that the single master server had to keep track of. And that's the trick. That's what made it possible for a single machine's memory to hold the entire map for a petabyte scale system.
And you can see this beautiful simplicity when you look at how a read works. The client just asks the master for directions one time. Where's this piece of data? After that, it talks directly to the chunk servers to get what it needs, completely cutting the master out of the conversation. It's just so fast and efficient. Now, writing data is a little more complex. It's kind of like a carefully choreographed dance. To make sure all the copies of the data stay in sync, the master picks one of them and says, "You're the primary." The client then sends the data to all the copies, but it only sends the final write command to that primary. The primary then figures out the exact order for the write and tells all the others, "Okay, do it now in this order." This makes sure every copy gets updated in the exact same way.
But look, this kind of elegant simplicity doesn't come for free. It came at a price. GFS was never meant to be a file system for everybody. Its highly specialized design meant making some very deliberate and, to some people, pretty shocking trade-offs. And this table really gets to the heart of it. This is GFS's relaxed approach to keeping data consistent. Look at that middle one, concurrent writes. The result is consistent but undefined. What does that mean? It means all the copies of the data will be identical, but they might be a completely jumbled mess from different clients all trying to write at the same time. Now, if you're a bank, that's a total disaster. But for Google's big data processing system, MapReduce, which could just filter out any junk data later on, it was a perfectly acceptable trade-off to get unbelievable speed.
And ironically, the system's greatest feature, its biggest simplification, that single master server, eventually became its biggest weakness. GFS was so successful that Google grew to a scale where the metadata, the map for all their files, just couldn't fit in one machine's memory anymore. The design, in a way, was a victim of its own incredible success. But that absolutely does not diminish its legacy. Not at all. So let's zoom back out for a second and just look at the lasting impact of this GFS philosophy. Because it truly did change how we build systems for the modern internet.
I mean, you can see the DNA of GFS everywhere you look today. The Hadoop file system, HDFS, is basically a direct descendant. That core idea of separating the control plane from the data plane, that's fundamental to all modern cloud storage, and even to systems like Kubernetes. And that focus on append-only workloads, it lives on in things like Apache Kafka. GFS really did provide the blueprint for so much of what came next.
And at the end of the day, this brings us to the ultimate lesson of GFS. It was so successful because it was never trying to be the perfect system for everyone. It was designed with a laser-like focus on solving Google's very specific problems at a very specific time. It's just a masterclass in pragmatic engineering and making smart, intelligent trade-offs.
Which really leaves us with one final big question. GFS solved its problem by completely rethinking the fundamental rules of failure and consistency. So, when you look at the challenges we're all facing today, what impossible problems could we solve if we were just willing to do the same thing?